All right, let's start. So we proved that the four conditions for a function between two metric spaces are equivalent, that f is continuous, inverse image of every open set is open, for any sequence converging to some element x, the image converges to f of x, and finally, for any closed subset y, uh, a of y, the inverse image is closed in x. All right. Now we will show something. Uh, well, I will define so-called uniformly continuous functions. Okay. So here's the definition. Uh, a function f from metric spaces xd and y rho is called uniformly continuous. Uniformly continuous. If the following happens, if for any epsilon positive there is some delta positive so that so that so that the x1 x2 is less than delta implies rho f of x1 f of x2 less than epsilon. Okay, you may wonder, what is different, uh, why this is different than the previous continuity definition, right? The difference is this. In the previous definition, we first fix a point x and then we take an epsilon ball around f of x, and then I try to find a delta ball around x, that pre-chosen point, so that the ball, the delta ball around x is mapped to the epsilon ball inside the epsilon ball around f of x. But here uh, we are given an epsilon, there is no x around, and I find a delta so that this delta works for every x. Namely, if I take any x and a delta ball around that x, it is mapped to the epsilon ball around f of x. So here, uh, or equivalently, the delta ball around f of x1, let's say, is mapped into the uh, epsilon ball around f of x, right? And here, okay, I should say the delta ball. Here, uh, delta is a function of epsilon only. It depends on the epsilon. It is it can be chosen uh, independently from uh, x. Okay, Here I have to be careful. Yes. So what happens is this. Uh, you give me an epsilon given. We find some delta so that whenever 2 points is has distance less than delta, so if this is less than delta, then the distance between f of x1 and f of x2 is less than epsilon. Okay, given delta, given epsilon, I can find such a delta. In case of continuity, you first you are first given a point x, and then for any epsilon you find a delta, and delta depends not only epsilon but also x. Okay, so that's the difference, and this is the reason why this is called uniform continuity, because the delta you choose works for every x. Okay, this is called uniform continuity, since the delta works for for all x in x. Okay, once epsilon is given. So you give an epsilon, I find a delta, and this works for all x. But in case of continuity, for each x, you may have to find a different delta. Okay. Now, so I said, several times that this continuity is different than the usual continuity. Let's see an example of that. Consider the function f from real numbers with absolute value metric to real numbers to absolute value metric with absolute value metric, given by f of x equals x squared. Okay. Well, claim is this function is continuous. We already know that because x is continuous, therefore x times x is continuous. Since f of x is just g of x times g of x, where g of x is this function, and g is clearly continuous, you can just take delta to be equals epsilon is continuous, f is continuous. By the way, actually I didn't prove something like this, right? If I have a continuous function from if I have two continuous functions from R to R, then their product is continuous. But this results from what? This results from limit definition, right? If G has limit, then G times G has limit, therefore F will have a limit, right? It follows from limit definition of continuity. limit characterization of continuity. Okay, so this is continuous. Or you can just show directly using epsilon delta. But claim is this, f is not uniformly continuous. Or maybe let me show that this is continuous using the epsilon delta definition. Okay, for the sake of completeness, let's prove that f is continuous using epsilon delta. Okay, take any x0 in R and epsilon positive. Okay, I have to prove what? I have to prove that f of x minus f of x0, which is just x squared minus x0 squared less than epsilon, right? But this is what? This is x minus x0 times x plus x0. Okay, now here is x0 and x is somewhere here. If I choose this interval of length at most 1, then x and x0 will be what? It will, this will be less than uh, x plus 1. So x plus x0 will be less than, right? So this will be x is at most x plus 1. Okay. Yeah. Okay. So x0 plus x0 plus 1. So 2x0 plus 1. So if I choose, okay, I want this to be less than epsilon. So this thing is less than 2x0 plus 1. So if I choose this to be less than epsilon over 2 times x0 plus 1, then this will be less than epsilon. So I need to choose my delta to be less than epsilon over 2x0 plus 1. Okay, so that's the strategy. Let's write it down. I am given x0 and epsilon. Okay, uh, choose delta to be what? Uh, Delta to be uh, epsilon over 2 times x0 plus 1. Okay, minimum of 1 and epsilon over 2 times x0 plus 1. Okay, then you see my delta depends on epsilon and x0, right? Note that, let me write in parentheses, note that uh, our choice of delta depends on epsilon and x0. Okay, now if x minus x0 is less than delta, then x minus x0 is certainly less than 1, right? Hence x minus x0, right? This is less than, remember, this thing is less than x minus x0 in absolute value, and this is less than 1, and therefore I have absolute value of x is less than 1 plus absolute value of x0. So, uh, so uh, x plus x0 is less than this gadget, and this is less than 1 plus x0. This is less than x0, so 1 plus 2 times x0. Now, if again uh, x minus x0 is less than delta, then f of x minus f of x0, which is x squared minus x0 squared, and this is just x minus x0 times x plus x0. But you see, this implies what? F of x minus f of x0. I assume that this is less than delta. So this is less than delta. X minus x0 is less than delta. But if x minus x0 is less than delta, I know that this second expression here is less than 1 plus 2 times x0. So 1 plus 2 times x0. But delta is chosen to be minimum of these two. So delta is less than this expression. So this is less than epsilon over 1 plus 2 times x0 and 1 plus 2 times x0. So they cancel and I obtain only epsilon. So this means f of x minus f of x0 is strictly less than epsilon. So what we have obtained is then, okay, I started with any x0 and epsilon. We choose some delta so that if this is less than delta, then uh, fx minus f0x is less than epsilon. Okay. Hence, f is continuous at x0. So we are done, right? But let me mention one more time that my choice of delta depends on both epsilon and x0. Okay. Note that delta is a function of x0 and epsilon, okay, which is the minimum of 1 and then what was it? 1 plus 2, no, epsilon over 1 plus 2 times x0. Right. Yes. So this function from real numbers to real numbers, taking x to x squared is continuous, but I claim that it is not uniformly continuous. So claim f is not uniformly continuous on R. So what I claim is this. This delta cannot be chosen independent of x0. It cannot be a function of epsilon only, okay? If you do so, you will have in trouble. So how can we prove this? Proof. I claim that I cannot choose this epsilon as a function of, I cannot choose delta as a function of epsilon only. So I must prove the following. So we must prove the following. Must prove there is some epsilon so that so that so that for any delta positive there is some point x0 so that, or maybe I should say x1 x2 so that so that x1 minus x2 are delta close to each other, but their images f of x1 and f of x2 are not epsilon close. So this is larger than or equal to epsilon. Okay. This means what? I can find some delta. Actually, so there is some epsilon so that no matter how small you choose your epsilon, I can find x1 and x2 so that this difference is larger than epsilon. Okay, you may need to think about this, formulation. Why, to show that f is not uniformly continuous, I have to prove this. Well, actually, the reason is simple. Uh, f is uniformly continuous means what? For any epsilon, I need to find a delta which satisfies this for all x1 and x2. So if it is not uniformly continuous, then there should be some delta so that there should be some epsilon so that this doesn't happen. Okay, and so that's what I will do now. But before I continue, let me show you why this is actually easy to see on the graph. Remember, recall the graph of f, right? This is the function uh, f of x equals x squared, right? It has a graph like this, a parabola, and I claim what? There is some epsilon. Actually, just take epsilon to be 1. Actually, any epsilon works. For any epsilon, I can find such a delta, but let me just take epsilon equals 1 because it is enough to find just one epsilon. I will show what? No matter how close x1 and x2 will be, I will find x1 and x2 which are delta close as you want, but their images will be at least 1 unit apart. How can I do this? Well, suppose your delta is something like this. Okay, I'll just take this interval, put on the x-axis and try to move it. Okay, If you choose your epsilon like this, then of course this distance sorry, this distance will be less than 1. But if I move this delta interval to the right or left, suppose it's somewhere here, okay, the same interval, just shift it. You see this time its image here, and this image is somewhere here, and the distances between these 2 points will be, right, larger than 1. Okay, this might be less than 1, our epsilon, but this will be larger than 1. And if you move further to the right, the distance will get larger and larger. Okay, that's the idea. So okay, so I took epsilon equals 1. Let any be given, delta positive be given. I need to find x1 and x2, okay, the endpoints of so 2 points which are delta close to each other. How can I do that? Uh, well, I need to just write down. I need to write down the inequality they have to satisfy. So f of x1, f of x2. This is x1 squared, x2 squared, and I want this to be larger than epsilon, which is 1. Okay. What is this? This is x1 minus x2 and x1 plus x2. Okay, this will be less than delta. So this should be, right? This should be, okay. This should be larger than 1 over delta. So if I choose x1 and x2, both of them positive and larger than 1 over delta, then I will be done. Okay, so let me do this as follows then. Right, I need to choose x1 and x2 both larger than delta. So you see, I first write down what I need to show, and then I'll choose my uh, you know uh, stuff accordingly. So remember what I have to do. For any delta, I need to find an x1 and x2 so that they are delta close, but this is larger than epsilon. Okay, now choose x1 to be 1 over delta and x2 x1 plus 1 over 2 delta. Then the difference between x1 and x2 is how much? Well, x1 and x2, this is just 1 over 2 delta. Uh, wait a minute. Yok. Sorry. Delta over 2. I need to. Okay, so this is delta over 2, which is less than delta. Okay. So given any delta, I choose x1 and x2 so that the difference between these two is less than delta. However, f of x1 minus f of x2 is how much? This is uh, uh, so x1 squared minus x1 plus delta 2 over squared, right? Which implies what? F of x1 minus f of x2. If I open this up, I will get x1 squared minus x1 squared. So minus 2x1 delta 1 over 2 plus delta squared over 2. Yok, bunu böyle yapmayacaktık. I'm sorry. We need to do this as follows. Şöyle yapacaktık. Sorry. x2 squared. So x1 minus x2, x1 plus x2, right? This is just delta over 2. But what about this? What about this? X1 and x2 are like this. So this is 1 over delta plus 1 over delta plus delta over 2, right? You see, this is larger than the following. Delta over 2 times. If I choose something less than this number, so this is 1 over delta, 1 over delta. Let me just cancel, delete this. I will get, these are all positive, 1 over delta plus 1 over delta. So this is just 2 over delta, which is 1. Okay, so this difference is strictly larger than 1, which is my epsilon, and this finishes the proof. Prove that f is not uniformly continuous. Okay. Do you have any questions so far? It is good to keep this picture in mind, okay? You give epsilon, no matter how small you choose your delta, if you move this interval to the right, the length of the delta interval is mapped will get larger and larger, and at some point it will exceed your epsilon, no matter what your epsilon is. Actually, in this case, I took epsilon 1, it will certainly pass 1 unit at some point, but uh, for this function, x square function, uh, actually it will work for any epsilon. Maybe you have to move further to the right, but at some point it will exceed your epsilon. So I gave the definition of uniform continuity, and then we have seen an example which is a continuous function, but it is not uniformly continuous. You may wonder, are there uniformly continuous functions? Well, there are actually many. So examples of uniformly continuous functions. For example, any linear function f from R to R is uniformly continuous. Let's see why this is the case. So what's a linear function? So let me say f is this form. Okay, a, b are some real numbers. Well, what is f of x1, f of x2? This difference. This is a x1 plus b minus a x2 plus b. So this is just a x1 minus a x2, and it can be written like a times x1 minus x2. So uh, if epsilon is given, then choose delta to be epsilon over the absolute value. Here, of course, I assume that a is not 0. If it is 0, then this is a constant function, and constant function is also uniformly continuous. But for a non-constant linear function, just choose delta to be this expression. Then if x1 minus x2 is less than delta, then f of x1 minus f of x2 is less than, right, a times delta, which is epsilon. So we are done. This is one example. Later we will see that indeed any continuous function f from R to I to R, where I, a closed interval like this, is a closed and bounded interval, is uniformly continuous. Of course, if this is a closed and bounded interval, you see that you cannot play the trick we used for x square function. There we moved the delta interval to the right. But in case your interval is bounded, you may not, you will not able to go to the right. You have to stop at some point. Therefore, that trick will not work. And actually, as I stated here, we will see that any continuous function on a closed and bounded interval is necessarily uniformly continuous. Okay, we will prove this. when we discuss compactness. Okay, what else? Consider this function again, f from R to R, f of x equals sine x. Okay. Uh, well, we know that you have seen this in calculus, right? We know that sine x minus sine y is always less than x and y, right? Hence, given epsilon positive, just choose delta to be epsilon. Then if x1, x2 is less than, or xy is less than delta, then f of x minus f of y, which is just sine x minus sine y, will be just less than x and y, uh, but that is less than delta, which is less than epsilon. Okay, hence f is uniformly continuous. Okay, all right. Okay. Uh, well, consider a function like this. Let me use a non-standard metric space. Let xt be a discrete metric space. Well, we know that any open set, sorry, any subset of X is open, right? Then any open subset, then any subset U of X is open, right? Every subset of a discrete metric space is open and closed. We know this. In particular, for any function, f from xd into y row, the inverse image f inverse of O will be open, right? For any open O in Y. Actually, this doesn't even have to be open, right? Because inverse image of everything is a subset and any subset is open. So inverse image of any open subset is also open. In particular, f is continuous, right? In particular, f is continuous. Well, this is a very interesting fact, right? If you have a function defined on a discrete metric space with values in any other metric space, then this is a continuous function. No matter how f is given, no matter y is which metric space, it is always continuous. Okay, actually more is true. More is true. Indeed, any function f from xd into y row, xd is of course discrete metric space, is uniformly continuous. Well, why is that? Well, let epsilon be given. I need to find a delta so that any 2 points which are delta close to each other will be mapped to 2 points which are epsilon close to each other. Okay, just take delta to be 1 over 2, which is a positive number. Then if x1 and x2 are delta close to each other, then you see what? Well, this is the discrete metric. So it takes only two values, either 0 or 1. This value, whatever it is less than 1 over 2, so it must be 0. Then the x1, x2 must be 0 because this is the discrete metric. And hence, x1 is equal to x2. But then, however, in this case, what is row of f of x1, f of x2? Well, they are the same, so this is row of f of x1, f of x1, which is just 0, and this is certainly less than epsilon. So what we have obtained is then, you see, I started with any epsilon, I found some delta, so that if this distance is less than epsilon, then this distance is less than epsilon. Okay. Hence, f is uniformly continuous. Okay, so on a discrete metric space, every function is continuous. Actually, more than that, every function is uniformly continuous. Of course, by definition, if a function is uniformly continuous, then it is continuous because you can find always delta, and in case of uniform continuity, this delta works for all x, right? It just depends on epsilon. All right, so let me stop at this point.